Hi everyone, welcome to Primary Sensors and Transmitters ELC 101. We're going to be covering Chapter 9, okay? In this chapter, we'll review all of the individual control elements in the control loop and how they communicate with each other, okay? And that's basically what this is about, transmission and communication, okay? Now, pressure transmitter integrally mounted to a sensor. Let's look at this particular transmitter. Right here is the sensor. It's in the line. And then it transmits its information directly to the transmitter. So it senses it, measures the process variable, and then it produces an output to the controller. Now, there are different ways that elements can perform sensing. So they measure, they sense, and then they measure, and they can act in tandem, okay? So the sensor detects the process variable, and the transducer converts the energy from one form to another. Now, I want you to understand transducer. In this particular instance, back in the day, transmitters and transducers were considered the same. They basically took information and then they basically converted it to readable information to the next element downstream. But we're really not going to call it transducers transmitters, okay? Transducers are going to be for us after it comes out of the controller and what it's going to tell either the control valve or a solenoid valve or whatever to do, okay? Like we talked about them last time, there's all different kinds of transducers. So here we're looking at a sensor-driven, an electronic loop. The sensor serves as the transducer and then provides input directly to the controller. In a transmitter-driven loop, the transducer is part of the transmitter and then converts the process variable into the standard electronic signal. Okay. All right, let's talk about different sensors. Primary sensors detect the process variable. That's just what they do. They must be able to respond accurately, precisely, and quickly, because that's what you want to do. You want to have good control and you want to be able to manipulate the variables and respond as well as possible. Now, the sensing elements come two ways: a discrete, standalone, or an integrally mounted one. The discrete is like your thermocouple or your RTD. You saw them in the lab. You had a couple of wires that are just down a thermal well. They're in the actual process element and they're detecting a temperature. Sometimes they're detecting a resistance. So they're both sending signals and then that goes to a transmitter. And then the transmitter takes those readings and converts it. Here you have a pressure transmitter. So the DP sound transmitter is one that is integrally mounted, as we just saw in that other picture. Okay, the sensor and then the transmitter are one. All right, so that's how that works. Now the transmitter, it's important to understand, provides a standardized signal that is accepted by all other instruments in the loop. And it's generally going to be the 4 to 20 milliamp signal. Okay. So it reads the process variable, it's sensed and measured, and then it is transducer converted by the transmitter circuit to the 4 to 20. So that's where they get this transducer word mixed up with transmitters. But we're going to look at a transmitter and a transducer in a different way. Okay, so again, you could have a primary sensor with it, or it could be integrally mounted together, or separate, and then added to it. Okay, let's look at the differential pressure transmitter itself. So a DP cell is a special type of sensing and measuring component. It's designed, right, to measure the difference between two different pressures, a high end and a low end, or actually high here, low here, or on the pressure sides in a flow. Okay, it can give you individual pressures at each point. So it can give you pressure and then it can give you the DP or the delta P, which is the difference. And that's generally what you look at. Now, there is a transmitter inside, and it does the transform. It does it and converts the signals, usually a 4 to 20 milliamp, and it can do a 3 to 15 pounds if you're working an actuator. But in this particular instance, we're not going to do that. We're just going to usually be going to a controller. It is the single most commonly used transmitter in the processing industry because not only does it do pressure at each tap point and the DP, it can also infer flow, level, and even density. This is an error. Okay, so that's what's important, and you see it all the time. Okay, so now let's talk about the information again. So here is our sensing element, our transmitter going to the controller. The controller takes an output, sends it to an actuator, in this particular instance, which then converts from the actuator takes the pressure and converts the instrument air to respond for this control valve. Okay, and it may be a solenoid, it could be an on-off switch, and going to a solenoid valve and so on, or a pump. But we're going to mostly be looking at control valves right now. Okay, the transmitter signal, regardless of the type or the magnitude of the process variable, again, its output is one of the most common standard instrument signals, 4 to 20 milliamps. So if you have a thermocouple with a millivolt input, or an RTD with that resistance input, pressure or analytical measurements, whatever they may be, flow, level, all of these process variables are converted into a standard instrument signal that gives you 0 to 100% of their measurements, okay, and then converted to the 4 to 20 milliamps. All right, now we're going to talk about scaling next. I have another PowerPoint for that because we're going to do some of the math. There's a lot of math involved in that. I want to make sure you understand it. So that's the second PowerPoint to this lesson of this week, okay? We'll come back to that. Now again, we want to remember, right, when we talk about the scaling, you go from, we're just going to take 0 to 100%, okay? So 0 is always 4 milliamps or 3 psi, and 100% is always 20 milliamps or 15 psi in this particular instance. And again, from the transmitter, it's always going to be 4 to 20. Now, if you have a pneumatic signal, this is just a refresher from the last chapter that we just talked about, the last PowerPoint. You have a slow to respond, and it's kept to short distances, okay? But electronic is constant throughout, and it can travel a long distance. And again, we're going to use electronic to go to the controller. Now, a live 0, remember we talked about this as well. A couple times people have asked, why do we start at 3 psi as 0% or 4 milliamps? So again, if you have a loss of power, you wouldn't know that if you had this at 0, okay? But if it's at 4, then you know, and you're at 0%, you know that it's not the power. You have power supply to your instrument, so there's something wrong maybe in your calibration. So it does allow for better troubleshooting and calibration. Same with your instrument error. If you lose instrument error and it was 0 and 0, you wouldn't know that. But if you lost instrument error and this is 0, but it's not 3 and it's 0, then you know, oh, I don't have any at all pressure to my instruments. So I have to make sure I go and fix that. So this again is important to understand for those two reasons. Okay, now we're going to jump into transducers. A transducer is a device, again, that converts one form of energy to another. So we talked about this in transmitters, right? But in this particular instance, we're going to say it's coming from, this is a little, again, confusing. Sometimes the sensor and the transducer are one and the same. That's if it's a transmitter, but we're going to be talking about transducers in the form of being actually generally something that feeds to this part here, the end final control element. Okay. All right. So the most common instrument signal transducer is the I to P transducer. Remember, we talked about them. There's I to P, P to I to E, E to I, and so on. There's all the different ones we listed. And we're going to be focusing on, in this particular instance, we're doing on the 4 to 20. Okay. I'm sorry, the right mechanical, the I to P current to the PSIG. If you look on page 163 of your text, I was flipping to that. There are the different types of transducers. We've talked about pneumatic to current, P to I, pneumatic to voltage, P to E, voltage to pneumatic, E to P, analog to digital, A to D, and D to A, digital to analog, and then of course I to P. Okay, so we're going to be looking at I to P, where we take this signal coming from the controller, it's 4 to 20 milliamps, and then it converts it into a pneumatic signal, 3 to 15. It is required in almost every electronic control loop in this field because it is commonly used to control valves pneumatically actuated. Okay, hold on, I gotta just pick this up. Okay. Now, transducers and pneumatic electronic signals. Two of the most commonly used instrument signals in the processing industry are the 4 to 20 and the 3 to 15. Even the most modern smart transmitters, which are microprocessor based, usually give you a 4 to 20 output. So again, these signals have what we call the live 0, which we just talked about, which means the signal's low range value is greater than the true 0. Okay, so I just wanted to, again, bring that up. And if you look at page, when you're doing your work, if you look at page 186, it goes into more detail again about the live 0 and why it's important. Okay, let's see how this relates to our control schemes and control loops. So in summary, when you're observing a control loop in the field or in a schematic, always start at the point of measurement. So here we would be looking at PT1003. It is the process variable that you're monitoring and you're wanting to manipulate or control. So if your PT transmitter is off, okay, then your PIC will be reading something off, and it could also be conveying information that is incorrect to your PV, which is your process valve, the control valve. Okay, so that's just why it's really important to make sure I understand that. Okay, now I'm going to go to the next PowerPoint in this series. Okay, so the second one is on scaling. Okay, talk to you soon.